Welcome to this webinar with the title How Error Correction IP Provides More than 20 dB Improvements of Time-Interleaving Spurious Effects in High-Speed ADC Systems. In this webinar, we will highlight the possibilities of digital error correction in gigasamples per second analog to digital converters. We will share some insights in so-called time-interleaved ADCs and illustrate the effect of mismatch and mismatch error correction. We will further demonstrate mismatch error correction using the commercially available Teledyne SP Devices IP core ADX. ADX is used to enhance the performance of the latest wideband 5.4 gigasamples per second 12-bit ADC of Teledyne E2V called EVAS350. High-resolution gigasample per second ADCs have experienced quite an increased commercial use during the last decade, going from specialty converters for certain T&M applications and defense-oriented applications to a broader deployment. Newer application areas include multiple use cases with time-of-flight technology, spectrometry, various instrumentation applications, and microwave frequency communications. Further, scientific installations conduct advanced large-scale experiments requiring multi-channel high-performance data acquisition. From an analog integrated circuit technology perspective, however, increasing sampling speeds of single-core ADCs without sacrificing resolution is a severe challenge. The technique of time-interleaving originates from the early 80s. Here, several ADC cores are used in order to increase the overall sampling frequency. This technique has regained renewed interest and is now broadly adopted in gigasamples per second analog to digital converters. Time-interleaved ADCs is today used commercially for all higher resolution converters with sampling frequencies exceeding 1.5 gigasamples per second. So now let's look at the concept of time-interleaving in more detail. In this picture you can see the basic principle of time-interleaving in the particular case when 4 ADC cores are used. In such an array of ADCs, the data converters take turns in acquiring samples. If each ADC core is operating at the boundaries of its capabilities, the overall time-interleaved ADC array can achieve sampling rates beyond what's possible using only one single ADC core. In the picture, the different ADCs and samples are color-coded to illustrate how the sampling is interleaved in time. In theory, this principle is a great way to extend the sampling rate by using a sufficient amount of ADC cores in order to reach a targeted sampling frequency. There are, however, two main practical limitations. One limitation is the input bandwidth, which actually tends to reduce when increasing the amount of ADC cores. Adding more ADCs means adding more parasitic capacitance to the input node, and for a targeted input signal swing, the input bandwidth will be limited. This makes the time-interleaved system suitable only for oversampled applications for the use of a large number of ADCs in the array. Achieving sufficient input bandwidths in the time-interleaved ADC structure is typically accomplished by using amplifiers or sample-and-hold circuitry in the front-end design. A second practical aspect of time-interleaved ADC that is also the focus of this webinar is the mismatch between the ADC cores. For error-free operation, a time-interleaved ADC system requires all M ADC cores used to behave identically from an input-output perspective. On this picture, M equals 4. Practical limitations in circuit manufacturing and device-to-device matching introduce errors which degrades the performance. These errors are mainly differences in gain and phase delay versus frequency between the ADC cores, as well as DC offset mismatches. On this slide, the effects of mismatches in time-interleaved ADCs are illustrated in the time domain as well as in the frequency domain. The ideal behavior of a 4-way time-interleaved ADC is shown in the top left figure. The 4 color-coded ADCs are taking turns in acquiring the sample sine wave time domain signal. The top right figure shows the corresponding direct delta function after applying the Fourier transform of the sine wave. The 3 main mismatch error types are shown in the bottom left figure. These will all contribute to samples being taken at undesired positions in the input waveform. It is very common to designate one of the ADC cores in the array as a reference and define mismatch in the way all the other ADC cores relate to this reference. A gain error means that an ADC core has a smaller or larger amplification than the reference ADC core. A phase delay mismatch means that an ADC core captures a sample at a different location horizontally than desired relative to the reference. In other words, a little bit too early or too late relative to the ideal sample position. A DC offset mismatch would mean that all samples taken by a specific ADC core have been biased a fixed amount of output codes relative to the reference ADC. In the frequency domain, gain as well as phase delay mismatch produces unwanted aliasing distortion that is interfering with the desired signal. Such aliasing means that differently frequency shifted copies of the input signal are added on top of the desired signal. This produces nonlinear distortion that can be quite severe for high resolution time-interleaved ADCs. In the frequency domain illustration of mismatch in the bottom right figure, the aliasing distortion is illustrated by 3 red copies of the desired signal spectrum. DC offset mismatch does not produce copies of the input signal. Instead, it introduces undesired tones at certain fixed positions in the spectrum. Now that we have a basic understanding of the types of mismatch and its effects, we can ask ourselves if mismatch errors in time-interleaved ADCs are really something to be considered seriously. On this slide, we take a deeper look at the phase misalignment in a 4-way 4 gigasamples per second time-interleaved ADC. The simplest form of phase delay mismatch is a frequency-independent time skew between the actual and the ideal sample position in a time-interleaved ADC. The negative effect of a phase misalignment between an ADC core and the reference ADC will actually grow worse with input frequency. If we consider an even number of ADC cores in total, one can show that the worst case aliasing of a multi-core time-interleaved ADC array is for the special case where the mismatch errors align themselves to make the system effectively operate as a 2-way time-interleaved ADC system. The worst case effect of a time skew mismatch is shown in the bottom left figure for different time skew mismatch errors. The time skew mismatch is defined as a fraction relative to the system sampling period. In the Nyquist frequency, that is 2 GHz of the 4 gigasamples per second time-interleaved ADC system considered, an unbelievably small time skew of 8 femtoseconds is in fact required in order to guarantee a worst-case aliasing level of 80 dBc. This corresponds to the electrical propagation delay of 1.2 micrometer wire. We're not considering the worst-case situation, but rather a more uniformly distributed time skew error. Monte Carlo simulations can provide a good idea of the achievable performance. The bottom right histogram shows such simulations for uniformly distributed time skew of 0.01% and 0.1% of the sampling period respectively, as well as the worst case aliasing for each case corresponding to the blue and green curves in the left-hand plot of the 2 GHz input signal. For both 0.01% and 0.1% time skew, most simulated mismatch situations are some 8 dB better than worst case. However, outliers do indeed approach the worst case limit. In gigasamples per second ADCs, sampling periods are in the hundreds of picoseconds range. Targeting a 75 dBc SFTR, being below 0.01% time skew is necessary. A timing alignment of a few tenths of femtoseconds is thus required. We can conclude that such requirements are extremely challenging. Now we have understood that what is really required to avoid aliasing from gigasamples per second time-interleaved ADCs is a few tenths of femtosecond alignment. Such requirements are beyond the robustness and accuracy capabilities of analog circuits. Luckily, digital logic is inherently robust and can be made arbitrarily accurate. Digital mismatch error correction is a solution that has been proven to work well in practice for multi-core time-interleaved ADC systems. Digital signal processing logic that performs mismatch error correction in time-interleaved ADC arrays does perform a post-processing error correction of the output data. In the block diagram on this slide, one can see the typical situation where the post-processing mismatch error correction block is placed directly after the time-interleaved ADC array. The main objective of such logic is to manipulate the sampled signals coming out of the ADC array such that the produced output signal will contain significantly less mismatch errors than the raw data. Practical implementations of such mismatch error correction exists in commercially proven mass-produced ASICs as well as FPGA instantiations. Teledyne Signal Processing Devices provides a commercial digital post-processing IP core for mismatch removal called ADX. This IP core identifies and removes the mismatches between all ADC cores in a time-interleaved ADC array. It does this in real time and is available for FPGAs and ASIC implementations. The IP core ADX uses a unique patented signal processing technique to remove mismatch errors that vary over frequency and temperature. On this slide, we show a typical 4-way time-interleaved ADC output signal spectrum. The left figure shows the amplitude spectrum for a 2-tone test signal and the 3 aliasing spectra from gain and phase delay mismatches, as well as 2 DC offset mismatch spurs, one in the center of the Nyquist band and one at the right edge. The output signal spectrum after ADX digital post-processing is shown in the figure to the right. The effect of mismatch is clearly suppressed. Looking a little deeper into how ADX works, the IP core uses a time variable interpolator that recomputes the sample values such that they are free of mismatch. This part of the signal processing is run in real time in the block diagram shown as the real-time signal reconstruction. In order for this reconstruction to produce an error-free signal out of the input signal containing mismatch errors, the real-time interpolator needs a model of the mismatch provided by one additional block. This block does either estimate the mismatch model parameters using the ADC array output signal or contains calibration data stored in the production of the device. In order for the calibration to be efficient both in terms of hardware resources and in production, a so-called model-based calibration can be used that we will talk about later in this webinar. Time-interleaved ADC mismatch is in general quite sensitive to temperature. How sensitive depends on the specific details of the implementation, but it's common that only a few degrees of temperature drift will change the properties of the mismatch noticeably. Thus, all approaches to mismatch error correction need to handle temperatures that change. In ADX, this is either managed by an adaptive mismatch model parameter estimation or by a model-based calibration. A property of time-interleaved ADC mismatch error correction that is central to its success is the ability to compensate mismatch errors over frequency. In practice, mismatch errors vary with frequency. On this slide we see an example of such variation. The figure to the left shows gain mismatch from a commercial 4-way time-interleaved ADC clocked at 3.8 GHz. As one of the 4 ADC cores in the array is used as a reference for the others, the gain versus frequency for that ADC core is a straight line at 0%. The other 3 curves show the measured gain mismatch relative to the reference, and it is clearly visible that the curvature of the mismatches versus frequency is quite significant. From the figure to the left, the worst case deviation over frequency for the gain mismatches occurs at 1770 MHz. The effect of applying optimal frequency-independent mismatch compensation is shown in the figure to the right. When compensating mismatch without dealing with the curvature of the mismatch versus frequency, one is limited to simply shifting the gain mismatch curvatures vertically. This is in practice implemented by manipulating the gain of each ADC core. From the right figure, one can see that after optimal frequency-independent compensation, the remaining mismatch can still be significant, and in this particular case, the SFTR improvement is merely some 6 dB. However, when the mismatch error correction is made to actually correct mismatch versus frequency, like in ADX, the improvements in SFTR can be an order of magnitude better. This slide compares optimal frequency-independent gain mismatch compensation for the measured mismatch shown in the previous slide with the results of ADX, which removes the mismatch errors versus frequency. The figures use the same scaling on the y-axis for the relative gain mismatch in order to clearly show the difference. The time variable interpolation and the accurate mismatch models in ADX remove the mismatches by compensating the mismatch over frequency, and the effective mismatch curvatures after correction become close to a flat line at 0%, thereby improving the SFTR to about 86 dBc. As digital mismatch error correction relies on good models for the mismatches in order to be successful, it is important to be able to identify and describe the mismatch accurately. ADX supports an adaptive blind background estimation where the mismatches are identified from the time-interleaved ADC array output data using signal processing. On this slide, we highlight the principles of how a frequency-dependent mismatch model is adapted to observations of mismatch in a time-interleaved ADC. This adaptation is applied to both gain and phase delay mismatch. The adaptation process is a perpetually repeated sequence which tracks mismatches over frequency and temperature drift. The blue curve illustrates the mismatch model, which in this example initially is set to a straight line. The actual mismatch is illustrated by the dotted line. In the presence of an input signal, observations are made of the mismatches for input signal frequencies of sufficient energy content. At step 1, two narrowband input signals allow accurate estimation of the mismatch conditions around these two frequencies, and the frequency-dependent mismatch model of the blue model curve is updated so that it captures the mismatch estimates in these two frequencies. As more input signal energy becomes available, such as in step 2, where a wideband signal is present, the mismatch is estimated at additional frequencies of sufficient energy contents, and the blue mismatch model is updated accordingly. The process continues and more input signals are applied to the blue mismatch model, and it approximates the accurate mismatch better and better. When the actual mismatch is changing due to, for example, temperature effects, the mismatch model will transition from modeling previous mismatch conditions to the new one. In this way, the mismatch model will track the actual mismatch conditions in a smooth way. A second alternative to establish the mismatch model parameters needed to reconstruct the mismatches within ADX is a model-based calibration. This is an indirect measurement of the mismatches that relies on the models of the mismatch behavior for a specific device. In production, a small subset of devices or systems are characterized carefully to capture the architectural error behavior over temperature and supply voltage. When calibrating each ADX instance, each device is subject to a simplified unit characterization, the result of which is stored along with the model parameters for the architectural behavior. At runtime, temperature and supply voltages are measured, and the mismatch model's parameters needed for compensation is computed based on the captured circuit behavior and the unit characterization results. This approach works well in mass-produced silicon, since each device test is simple and fast. An FPGA instantiation of ADX is available ready to use with Teledyne E2V EV12AS350, which is a 5.4 gigasample per second 12-bit wideband ADC. This ADC is a 4-way time-interleaved ADC, and when used with ADX4, the wideband suppression of aliasing distortion provides up to 20 dB improvement of time-interleaving errors. This makes the EV12AS350 and ADX4 combination the highest performance wideband 12-bit ADC solution on the market. This precompiled ADX4 version is available for exclusive licensing to users of EV12AS350. There is a ready-to-use evaluation board called EV12AS350-ADX4-EVM, which can be used to evaluate the combined ADC and IP configuration.
This is an overview of the EV12AS350 ADC from Teledyne E2V. It's a 12-bit 5.4 gigasample per second ADC and has approximately 4.8 gigahertz input bandwidth. As you can see in this simplified block diagram, there's a single input which goes to 4 track and holds and 4 ADC cores. These 4 cores are interleaved, each at 1.35 gigasamples per second to reach the 5.4 gigasamples per second rate of the complete ADC. On board is a precision timing block which generates the 90 degrees out of phase clocks that go to each of the track and holds and ADCs necessary to achieve the proper alignment for interleaving. All of the ADC configuration can be set up through an SPI interface that you see here on the block diagram. The cores are laid out to be very symmetrical. You see in the layout in the upper right corner here, and this die is packaged into a 380 ball EPGA that's 31 millimeters on a side. The output data, once the Signal is converted from analog to digital. The output data is output through parallel LVDS buffers, which are very low latency. Here's a bit more information on the EV12AS350. As I mentioned before, it's low latency. The latency through the whole converter is about 26 clock cycles, which is less than 5 nanoseconds when you're operating at 5.4 gigasamples per second. It has the capability of over 2.5 gigahertz of instantaneous bandwidth. The Nyquist zones are about 2.7 gigahertz. The analog input bandwidth is 4.8 gigahertz, and that's the 3 dB bandwidth. On this table, you'll see 3 different frequencies, about 2 gigahertz, 2.7 gigahertz, 4.2 gigahertz, and each of them we're running in a signal that's about 6 dB below full scale. We see effective number of bits here in the table, 9 bits at 1.9 gigahertz, 8.6 at 2.7, and just under 8 at 4.2 gigahertz. On the spurious free dynamic range spec, you can see we've got 69 dB full scale at 2 gigahertz, 65 at 2.7 gigahertz, and 55 at 4.2 gigahertz. The plots below this show some information relative to different signal amplitudes, 1 dB below full scale, 3 dB below full scale, and 6 dB below full scale, and give you an indication of signal to noise ratio and effective number of bits over frequency. In the next slide, you're going to see how some of this performance can be and is enhanced by ADX4. On this slide, you'll see some of the enhancements that can be achieved with ADX when using the EV12AS350 ADC. And to explain a little bit, we're using the gold ADC as the reference ADC, and then we're looking at mismatches before and after the application of ADX to the signal. So there's 3, the blue, the green, the red ADCs, and you can see the mismatch here in magnitude and in time. Each of these solid lines is the ADC's errors before we've applied ADX, and then these dotted lines that show the magnitude and phase or time mismatch after ADX is applied shows significant improvements to each of these 2 parameters when you're matching magnitude and time delays. An order of magnitude approximately mismatch error reduction is possible with ADX4, and so in the next slide we'll see how does that impact the actual spectrum of the signals.
In the frequency domain, the corresponding mismatch error correction effect is shown in the amplitude spectrum to the left. The top left figure shows the native ADC amplitude spectrum for a -1 dB full scale close to mid-band sine wave test signal, and in the bottom left figure the corresponding amplitude spectrum after ADX is shown. The aliasing distortion spurs due to mismatch are suppressed close to the noise floor of the device. In the figure to the right, the resulting SFDR improvement is shown when sweeping the input signal up to 2.4 GHz. Time-interleaving spurs are pushed down below 70 dB full scale, yielding an SFDR improvement up to 20 dB. The EV12AS350-ADX4-EVM evaluation board carries the EV12AS350 and the Xilinx Kintex 7 FPGA containing ADX4. This unit is an out-of-the-box evaluation option for the combined solution. It supports an internally generated sampling clock as well as an external clock signal and has a reference input for the generation of coherent test signals. The EVM schematics is available as a reference front-end and clocking design for the ADC. The board has a USB 3.0 interface and a 12-volt power supply. It comes with AD Capture Lab data acquisition and analysis software that is easy to install and use. Users can also store taken data before and after ADX to file or of different formats, and Python scripts are available to use in scripted testing where data is streamed to host PC. We will now show a brief live demonstration of the EV12AS350-ADX4-EVM. In this test we have connected the EV12AS350 to a sine wave generator, and we will use the AD Capture Lab software to illustrate the performance of the combined EV12AS350 and ADX4 solution. The EVM software plot both time dynamic performance and time-interleaving spurs. We will look at the amplitude spectrum of the ADX4 output signal for a few input signal frequencies. Data is collected repeatedly, and from the measured amplitude spectrum, one can see that interleaving spurs are below 70 dB fs across the entire sweep. When the aliasing spurs reach such low levels, noise that is uncorrelated between different ADC core references cause small fluctuations in the aliasing tone levels. SNR in these measurements is influenced by the wideband noise of the signal generator that provides the input signal across the entire Nyquist band of the ADC. With ADX, the SFTR of the ADC is set by the harmonic distortion. ADX4 is available as a licensable IP core for FPGAs and CMOS ASICs. Blind background operation or manually calibrated mismatch models are used. Mismatch errors are compensated over frequency and temperature drift. ADX4 operates in several Nyquist bands, one at a time. A change in sampling frequency requires new background adaptation or reloading the model parameters. Total latency through ADX4 for EV12AS350 is 608 samples or 112.6 nanoseconds at 5.4 gigasamples per second, which makes ADX suitable for non-latency critical applications. A complete EV12AS350-ADX4-EVM evaluation kit is available for $5,700. So some recent questions from customers regarding the ADX4 are as follows. Is ADX customized for specific ADCs? The algorithms and implementations of ADX are generic and are capable of performing mismatch error correction for a wide range of time-interleaved ADCs. Customizations can be made if desired to further optimize the performance for a specifically targeted ADC. However, the precompiled ADX presented in this webinar cannot be licensed to enhance ADCs which directly compete with ADCs of Teledyne E2V.
So what we see here are some recent questions we've received from our existing EV12AS350 customers, and they're all related to how does ADX4 impact the performance, how does it improve the performance of the EV12AS350. So you see the first question here says, how much performance improvement does ADX4 bring to the EV12AS350? And the answer is, as we've measured this, we get up to 30 dB improvement in the interleaving spurs. They're driven down, way down. And when we do add ADX4, these spurs get down far enough that the dominant spurs, the spurs free dynamic range, is dominated by harmonics and other spurs. So you may see an SFDR improvement of about 15 dB. The interleave spurs are down 30 from where they were, so they are out of the picture. And so that's a big improvement and gets them out of the way. The second question here is related to latency. We talked about the latency of the EV12AS350 as being very low at 26 clock cycles. When you implement ADX4, it's usually in an ASIC or an FPGA, and so that delay will depend on the speed of those the processes used in the ASIC or the FPGA. But we did an actual measurement on this implementing ADX4 in a Kintex 7 FPGA from Xilinx, and what we got was about 608 clock cycles through the ADX4 in addition to the 26 clock cycles we saw through the part, and the net result is about 117 nanoseconds in that 634 clock cycles at 5.4 gigasamples per second. So ADX4 drives the spurs way down. It does take some time to do that, to do the post-processing of the signals to clean it up. The last question here is about calibration working over a wide temperature range, and when we actually do the calibration that's pre-programmed into these parts. In our final test program, we do set up several calibration settings. So one towards the coldest end of the temperature range, and another that covers the ambient or room temperature and hot temperature conditions. And the user, you can decide whether you want to use this, which set you want to use depending on your conditions and your signal, and the actual calibration settings can be changed by the user through the SPI interface. So when using the EV12AS350 with the ADX4 IP core, the mismatches between the internal ADCs are automatically corrected, but you can tweak that even further in your application. There's an app note on dealing with the interpolation and calibration techniques, and it's available on Teledyne E2V's product web page for the EV12AS350.
Thank you for attending this webinar. Please don't hesitate to contact us if you have any questions on the presented material.